Okay, I'm going to get started. Last class we talked about electric flux. It was a new concept. Today's class we're going to talk about electric potential. That's another new concept. Specifically, in today's class, I want to go through the few items that are listed on this overhead. I want to remind us about two different ways we look at physics problems. One is from the perspective of forces that are acting on objects. Another one is from the perspective of energy and flow of energy for those objects. So that's a bit of a reminder. It's a bit of a reminder from Physics 211, where you've discussed forces and energy. Then we're going to get on to introducing the idea of electrical potential and the definition of electrical potential. We give it the symbol V, that's electrical potential. We'll talk about the relationship, the connection between the electrical potential V, the new thing, and the electrical field of the electrical force and the old thing. And then we'll move on and we'll look at, and we'll do this on the way actually, examples, illustrations, problems involving electrical potentials and electrical energy. So that's really the plan. I wanted to start with a couple of slides. I've got one here and the next one about kind of analogies or metaphors or imagery in physics. We're dealing with abstract mathematical quantities in physics, and often it's helpful to have sort of images or analogies for those quantities. So we did this last class because we introduced the electrical flux, but we tried to think of electrical flux in the following way. We sort of thought of positive charges as a source, kind of a faucet for electrical flux and field. We thought of negative charges as kind of the sink or the drain of electrical field, electrical flux. And we imagined kind of field lines as the flow, the motion of the electrical flux from positive charges through space to negative charges. And so we had that kind of imagery of flux that's helpful for a rather mathematical, precise quantity like electric flux. We're going to do the same thing with electrical potential. So electrical potential is also rather abstract and mathematical and new quantity. But we're going to draw analogy with positive charges being kind of mountains or hills in an electrical landscape, negative charges being valleys or wells in a electrical landscape, and electrical field as kind of being the trails, those field lines being the trails or the paths from upstairs on the mountain near the positive charges to downstairs in the valley, the negative charges. So again, it's a bit of imagery or analogy that will help us imagine this abstract mathematical electrical potential. Okay, so I want to start with this reminder about the role of force and the role of energy in physics in general, and we'll apply it in our work on electricity specifically. So I got two slides here. I mean, they're really the same slide, and I've just modified the first slide to make the second slide. First slide's about gravity, something you met in 211. Second slide's about electricity, the new thing we're meeting now in 213. if you remember in the case of gravity, if we imagine we just drop an object, drop an apple, right? There's two ways of thinking about how gravity acts on that dropped object, on that apple. You can think about it from the force perspective, which is on the left-hand side of this slide, or you can think about it from an energy perspective, which is on the right-hand side of this slide. Up to now, in electricity, we've been working more with the force perspective, but we're going to start working with the energy perspective. So if we think about the falling apple from the force perspective, that's pictured over here on the left, then that dropped apple has, by virtue of its mass, it experiences a downwards gravitational pull by the Earth. So this is the gravitational force. And it accelerates towards the Earth. And so that's the force perspective on the falling apple. The apple is falling under a gravitational force, accelerating under a gravitational force that's carried, mediated, conveyed by a gravitational field. I pictured the field here. The other perspective is kind of the energy perspective. In the energy perspective, in the case of the falling apple, we would think of two forms of energy. We would think of a gravitational potential energy by virtue of the apple's height above the ground. We would think of kinetic energy by virtue of the apple's motion. And when we think about the falling apple from the energy perspective, what we're thinking about is as the apple falls, gravitational potential energy, here I call it potential energy with the subscript G, is being turned into motion energy, kinetic energy. Here it is, Ke. And that's that transfer of energy from one form to another, from potential energy to kinetic energy, is achieved by the gravitational force doing gravitational work. So that's the movement of the energy, the flow of the energy. Work is flow of energy, movement of energy from one form to another form in this particular case. And so that's a quick summary of force perspective, energy perspective on something that's familiar, falling bodies. The same ideas, force perspective, energy perspective, can be applied in electricity too. And so this is the case of electricity. Again, I'm thinking about the force and energy perspectives. In this case, I'm not thinking about a mass falling under gravity. Look, I changed this a little bit of the slide. I thought about a charge, Q, falling under electricity. But still, I drew this force perspective picture over here on the left. I drew this energy perspective picture over here on the right. If I think about the charge falling under electricity, maybe I should have put falling in quotes, but if I think about that charge falling under electricity, then that charge, by virtue of its charge, experiences an electrical force, I indicated it here, in a immersed in an electrical field, that causes an acceleration, and the charge picks up speed as it falls. And so that's the force perspective, and we've been thinking about that. Here's the energy perspective. In the energy perspective for our charge in motion under the electrical force, we have two types of energy again, like the gravitational case. We have a potential energy. This is electrical potential energy, so it's got the subscript E on it. We also have motion, so we've got kinetic energy, this brand of energy associated with movement. And from the energy perspective, as the charge falls under gravity, as the charge falls under electricity, electrical potential energy is being converted into, turned into moving energy, kinetic energy. We're not losing any, we're not gaining energy. The electrical force is doing some electrical work and moving electrical potential energy into kinetic energy. The charge picks up some speed, the charge loses some of its store of electrical potential energy. So that's the energy perspective. And so today's class is really all about taking some of that background from gravity and thinking of that in terms of force and energy perspectives, applying it to electricity and thinking about electricity perspectives in addition to force perspectives in that case. Okay, I want to show you a demonstration. I want to show you a demonstration that, well, the gravitational field that is responsible for gravitational forces, mediating gravitational forces, that contains energy, and energy can flow through that. And that's why we turn gravitational energy into kinetic energy. Likewise, the electrical field that mediates electrical forces, that contains electrical energy. It conveys, transports, mediates electrical energy. And I want to show you a demonstration that the electrical field kind of is real, that's the first thing, and also contains energy. I want to try and prove that to you. So to do that, I'm going to show you demonstrations kind of like this picture here. So this is an interesting photograph. In this photograph, there are a large number of vertically standing fluorescent lamps. And you can see they've been arranged in this nice array, someone's laid them out there, and they're all lit. But none of them is connected to any wires, to any power outlet. They're just lit, having been stuck in the ground. How could that be possible? The reason it's possible is that above this array of fluorescent lights or lamps are power lines. Now, power lines are the sources of electric and magnetic fields. But they're the sources of electric and magnetic fields. Those electric and magnetic fields store electric and magnetic energy. And it's that electromagnetic energy that's actually lighting these lamps. And so I'm going to try and demonstrate that I'm going to use the Van de Graaff generator. Remember, with the Van de Graaff generator, we can basically harvest electrical charge. So I can collect some electrical charge. I'm going to do that. And I got two lamps here. Here's a lamp, and here's another lamp. And we're going to try and light these by just bathing them in, by just immersing them in the electrical fields surrounding the electrical charges that we harvested on the Van de Graaff generator. So I'm going to try and do that. I've got to set the mood, though. I got to do two things to make a nice demonstration. And I've forgotten one of them. I'm going to turn the overheads off. And I'm going to turn the lights off. And I'm going to start the Van de Graaff up. And then this is one of the fluorescent lamps. I'm just going to bring it up. And I hope you, and I'm not touching anything. I've just got it close to, but not touching the Van de Graaff. And you see this, this is like Frankenstein's lab, right? This lamp is being lit by the energy that's stored in the electrical field. And so that's my proof to you that there is an electrical field associated with that charge, and there is electrical energy in that electrical field that's associated with that charge. I got a second lamp. Again, I'm not touching the Van de Graaff generator, but that lamp is being lit by being immersed in an electrical field that is a store of electrical energy. Okay, let's get the lights back on. And let's try and now we're believers in the concept of electrical fields and electrical energy, let's try and get mathematically rigorous with describing electrical energy, and in particular introduce this quantity called electrical potential. So on this slide, I'm reminding you of our definition of the electrical field. Remember when we defined the electrical field, we imagined what was called a source charge and what was called a field charge. The source charge was just any old arrangement or blob of charge that would create an electrical field. And then the test charge was really the probe of the electrical field, how we were going to define the electrical field. We put the test charge nearby the source charge. We put the test charge in the electrical field of the source charge, and knowing the charge on the test charge, we called it Q naught. Measuring the force on the test charge, we call it F, the electrical force. We were able to define the electrical field at the location of the test charge. We did it with this equation here. This was the field equation. So this equation tells us the electrical field at some point in space where we have positioned the test charge. The electrical field at this point in space where we place the test charge is equal to the charge of the test charge. We better know that. That's Q naught. And it's determined by the force on the test charge. We better measure that. It's the ratio of the force to the test charge. And so that defines the electrical field. That was a scheme for defining the electrical field, which is an abstract mathematical thing in terms of measurable things. So we can measure the charge on the test charge. We can measure the force that's experienced by the test charge. Therefore, we can infer the underlying electrical field that's creating that force. We do the same thing for electrical potential. Again, we think about a source charge, and we think about a test charge. We think about the source charge now as the source of an electrical potential that's surrounding the source charge, that's due to the source charge. And we think about the test charge as kind of the probe, the way we're going to explore, examine, measure that, determine that electrical potential. So I pictured that all upstairs here. So again, we're thinking over here on the left of the source charge as being a source of electric potential V. We're thinking of the test charge as being the probe of the electrical potential V. And we're going to, like the field equation, where we define the electrical field, we're going to use a very similar looking equation where we define the electrical potential. It's this equation here. So the last equation, I would call that the field equation. This equation here, we don't call it the potential equation. I don't know why. But it plays the role of the field equation, but defines the electrical potential. Actually, there's an important point here. The equation that define the field at a single point, the location of the test charge. So wherever you wanted to know the field, put the test charge and measure the force on it, and that will tell you the field. This equation works a little different. This equation defines the difference, the change in electrical potential between 2 points in space. So the equation involves 2 locations in space and the difference in potential between those 2 locations. You can see that in the diagram upstairs here. Instead of just putting the test charge at some single point to measure the field, I actually started with the test charge at some initial location. I moved it to some final location, in that way to probe the difference in the electrical potential between those two locations. And so that's a difference, a subtlety about defining the potential. We're actually defining the potential difference. That's why there's this, I've not joined a sorority or anything. This is delta V. This is the change in potential between these 2 points. Okay. delta V, the change in potential, this equation tells us, is the change in potential energy when you move the test charge. So if you're going to move the test charge from one location to another location, that means you've got to you're going to be moving it closer to or further from the source charge. It's going to be storing more energy, or it's going to be releasing some electrical energy, storing more potential energy, electrical potential energy, or maybe releasing some electrical potential energy. So there's a change in energy when we move the charge from here to here, just like there's a change in gravitational energy when I drop the ball. There's a change in electrical potential energy, that's delta PE, and the electrical potential difference is just that change in potential energy divided by the value of the test charge. So that's how we define potential difference. And again, it's important that whereas the field was defined at a single point, electrical potential differences are just, they're defined as differences in potentials between 2 points. So that's very important. Okay. Again, this equation defining the potential difference is defining an abstract thing, electrical potential difference. That's as abstract as it gets in terms of more measurable things, like the charge that's owned by the test charge, like the work that you had to do, the energy you had to transfer to move the test charge in the neighborhood of the source charge. So it's defining an abstract thing in terms of more concrete, measurable things. Yeah?
So like for electric field, you know how like we also just changed it with distance? Like if we know the source charge, we didn't have to know the test charge, if we just knew the distance?
I think I get what you're getting at there. With the electrical potential, we had an equation for the electrical field as a function of distance from, say, a positive charge or a negative charge. So there is likewise an equation for the electrical potential as a function of distance from a positive and negative charge. So you basically interpreted what I'm going to say next. So we're going to move now we define the idea, the concept of electrical potential, like we had defined the idea, the concept of electrical field. We can ask the question, what is the electrical field? What is the electrical potential of the basic building blocks, like positive and negative charges? So it's exactly what we're going to do. That's a good point. Okay. I just wanted to stress, this is like the pitfalls of electrical potentials. Electrical field was abstract enough, I feel. You can't see it, but it is a hidden mechanism, mediator, conveyor of electrical forces. Electrical potential is even more abstract in a way. But again, it's a real thing that's related to the electrical energy that's stored by electrical charge. So I want to make a few points about it. As I say, the electrical field has a physical significance at any point in space. Any point in space we can say what the electrical field is. The electrical potential difference, it only has a meaning in it tells you the difference in electrical potential between any 2 points in space. You really can't define the electrical potential at a single point in space. You can only say how that point in space's potential is different from some other point in space. So that's a strange thing. There's a freedom with the electrical potential. I've written it down here. It's an amazing freedom, really. So the electrical potential is measured in volts. And you could choose any way you like, absolutely any way you like, to be 0 volts. And then that would just be a reference point. Something might be plus 1 volt with respect to that, or minus 1 volt with respect to that. But you could choose any way you like to be 0 volts. And so there's a freedom that comes with the electrical potential, that the only potential differences matter, but it's also a trap, kind of a trap that comes with the electrical potential, that you can choose 0 volts, what we call ground, to be anywhere you like. at your convenience. For point charges, we normally choose the electrical potential to be 0 volts, sort of very far, kind of infinitely far from a point charge, a positive point charge or a negative point charge. We'll imagine that 0 volts is very far away. On the other hand, we'll see cases where we've got plates of charge, a positive plate of charge and a negative plate of charge. In that case, it turns out to be convenient typically to define one or other of these two plates of opposite charges to be at 0 volts. So there's a freedom, but there's a complexity that comes with electrical potential. So this was to warn you about that. Okay, now let's look at the relationship, the connection between the electrical field, which is a mechanism for the electrical interaction, but also the electrical potential you can think of as a mechanism for the electrical interaction. So how are they connected to one another? This slide is going to demonstrate to us how the two are connected to one another. So that's the goal of this slide, is to demonstrate the relationship between V, the potential we just introduced, and E, the field we previously introduced. In the picture, I got a wall of positive charge over here on the left. I got a wall of negative charge over here on the right. It's just a convenient setup to define the relationship, to connect together V and E. So I've made that arrangement. And of course we know that the positive charges are sources of electric field lines. The negative charges are kind of the drains of the electrical field lines, the sinks of them. And so the field lines in this particular situation of a brick wall of positive charge on the left, a brick wall of negative charge on the right, just stream across from left to right, from the positive charges to the negative charges. So in orange here are the field lines. In this field, I placed a positive charge. Here it is. And in this field, if I was to release that positive charge, well, it's going to be repelled by the positive plate. It's going to be attracted by the negative plate. It's going to fly from over here on the left to over here on the right. And I've imagined that happening. So look, I'm imagining here the positive charges moving from this location on the left to this location on the right. And under this influence of the electrical interaction, under the influence of the electrical force. And all I'm going to do is write down a description of that from the perspective of forces and from the perspective of electrical potentials. And so I'm going to turn this picture into an equation. My goal is to turn this picture into an equation that on one side of it, this is the left-hand side, has kind of the energy perspective, and on the other side, the right-hand side of it, takes the force perspective. So let's start here. Over here on the left-hand side, I've written the change in electrical potential energy. So when the charge flew from the left to the right, it got further away from the repelling positive plates, closer to the attracting negative plates. There's a change in the electrical potential energy. It wants to fly over there. It actually wants to release electrical potential energy and turn it into kinetic energy, moving energy. It's just like the falling apple under gravity, this situation here. So there's a change in potential energy. That change in potential energy, we said, is accomplished by the electrical force doing electrical work. So here's the electrical work that's done by the electrical force, and I can write it as the work that's done by the electrical force, or I can actually write it, remember, work equals force times distance. So I've written it here as this work that's done, this change in energy, in terms of the force itself. It's the force times the distance, force times the displacement. And so this formula here magically connects our two worlds of energy perspective and force perspective. Now, at this point, if we want a connection between E and V, we want a connection between electric potential, electrical field, all I have to do is plug in the field equation. That's the guy over here. We had it 2 slides ago. Plug in the potential equation, the equation defining electrical potential difference. I've got it over here on the left-hand side. If I plug those 2 equations in, I get, and cancel out the charges, I get this expression here. This expression is the relationship between the electrical potential on the left and the electrical field on the right. It says that the change in electrical potential between 2 points is equal to negative, the electric field strength in the region between the 2 points, times the displacement, the movement between those 2 points. That's the delta x. You can turn that equation around. Instead of saying that delta V equals something, you can say that E equals something. If you turn it around the other way, it says that E equals minus delta V over delta x, but that has, we can describe that in words. That makes it kind of easier to imagine. That equation, that last equation, is saying that the electrical field is actually the negative slope of the electrical potential. So delta V over delta x is a slope, the rate of change of the potential in space. So it's the slope of the potential, and the field is that slope. It's the negative of that slope. It's the negative slope of the electrical potential. So if you've got an electrical potential that's just steeply changing, it's a steep slope, that's going to be a strong electrical field. If you've got an electrical potential that's gradually changing in your electrical landscape, that's going to be a weak electrical field. If you've got electrical potential that's just constant in your electrical landscape, there's going to be no electrical field. So that's how the electrical field, electrical potential are related. The way I always think about it is this visual picture that the field, the electric field, is that negative slope of the electrical potential. I think of the electrical potential as this electrical landscape with hills and valleys and all sorts of things like that. And then depending on how steep it is in that landscape, as I walk around that landscape, that's telling me, that's inferring to me the electrical field. If I'm going downhill, which is negative slope, it means that's a positive electrical field. If I'm going uphill, which is a positive slope of the potential, then that means that the electrical field is in the opposite direction, the negative direction. Okay. I think it's going to be handy to look at this in practice, right? Because I felt I'm going down a rabbit hole of abstraction here in defining electrical fields and relations to defining electrical potentials and relations to electrical fields. So let's try and make it a bit more concrete with this example. So on this figure, on this graph, I've plotted the electrical potential, that's the vertical axis, versus position in space. That's the horizontal axis here. So I've got position in space measured in centimeters, and I've got vertically electrical potential measured in volts. It looks like a boring old graph, but really this is an example of me describing a beautiful electrical landscape, right? This is an electrical landscape of hills and valleys, right? We've got a hill over here in our landscape. We've got a valley down here in our landscape. We've got a little bit of a plateau here in our landscape. This is an electrical landscape in an electrical world, and the graph is just describing that to us. So the graph is telling us that at the coordinate x equals 0, the potential is 0. It rises to 30 volts at coordinate of 1 centimeter. It falls back to 0 volts at this location 2 centimeters. It's then 0 until we get to 3 centimeters, and then there's this valley, this 30-volt valley that is deepest at 4 centimeters and then comes back up to sea level here at 5 centimeters. That's the landscape. From this landscape, we can infer, we can figure out what the electrical field is in the different regions. So I can look at this landscape of electrical potential. You can look at this, you're going to be trained to look at this landscape of electrical potential and be able to figure out in your head what the corresponding electrical field is. And the rule is that the electrical field is the negative slope of the electrical potential. So if you can see the slope of the potential, and we can all see where it's sloping up, sloping down, not sloping at all, you can see that slope of the electrical potential. You can essentially see you're seeing the electrical field. So let's just go through a few examples here. Let's take this first 1 centimeter section, right? This is a mountain in the electrical landscape, and here we are walking up that mountain. In between 0 and 1 centimeters, if we walk from coordinate 0 centimeters to 1 centimeters, the potentials change from 0 to 30 volts. So the slope is, remember, change in y over change in x. This is change in potential over change in x. So the slope is the 30 volt change in potential divided by the 1 centimeter change in position. So it's 30 volts per centimeter. Is the slope of the electrical potential. Now, 30 volts per centimeter are an alternate unit of electrical field. So it's going to tell us the electrical field. The only thing is, for the electrical field, we want the negative slope. So this was a positive 30 volts per centimeter because we went uphill. The negative of it is a negative 30 volts per centimeter, and that's the direction of the electrical field. So the electrical field in this region here has a strength that's 30 volts per centimeter towards the left in the negative x direction. What about walking downhill here? Well, again, just to figure out the electrical field, remember the electrical field is the negative slope of the electrical potential. So as you walk from location 1 centimeter, location 2 centimeter, you've changed the electrical potential from, it was 30 volts, positive 30 volts, it's now 0 volts. So the change of the electrical potential is minus 30 volts. So if we want the slope of the electrical potential, it's going to be minus 30 volts divided by 1 centimeter again. We just move 1 centimeter. So it's going to be minus 30 volts per centimeter. But remember, the electrical field is the negative slope of the electrical potential. So we've got to change the sign on that. So we're going to get positive 30 volts per centimeter for the electrical potential in this region here between 1 and 2 centimeters. And so the electrical potential here where the electrical field here has a size that's 30 volts per centimeter. Its sign is positive, meaning its direction is from the left towards the right. It's reverse direction here. Okay, so we've seen a region of an electrical field towards the left, a region of electrical field towards the right. Let's walk. Why not? Why not walk 1 more centimeter across this beautiful landscape of electrical potential? Let's walk from 2 centimeters to 3 centimeters. The electrical potential here doesn't change. It's always 0 volts. The change in electrical potential is 0 volts, so that means that the slope of electrical potential is 0 volts per centimeter, is 0, which means that the electrical field in this region here is also 0. This is a region of 0 electrical field. And we're able to read that off of that graph, understanding that relationship between electrical potential and electrical field. Okay. I think I have a quiz question. Yeah. So I'm trying to look at the clock. For some reason, my My watch says it's 1:15 right now. And I don't know why it's doing that, but it says 10:10. So
It's 10:45. Well, yes, computer.
okay, so this quiz question just asks you to do what I was doing for those first 3 1 centimeter steps, for the final 2 1 centimeter steps. So you got to figure out what is the electrical field, both size and sign, in this region here from 3 centimeters to 4 centimeters. What is the electrical field in the final region here from 4 centimeters to 5 centimeters? And then just pick one of these 4 possibilities here.
Can, baby. Nothing but trash bags.
Okay, let's talk about the answer to this one. So there's 4 possible answers we're given in this multiple choice. Look, they're all, the size of all the fields are 30 volts per centimeter. So this question isn't about the size of the fields because there's only one size of the field in all of the answers here, 30 volts per centimeter. It's just about the directions of the field. Because the answers differ in whether it's minus 30 volts per centimeter or plus 30 volts per centimeter. In this region here from 3 to 4 centimeters, the slope is downwards. That's a negative slope. The electrical field is the negative of the slope. It's the negative of the negative slope, so the electrical field is positive. It's pointing from the left to the right. So 3 to 4 centimeters is plus 30 volts per centimeter. In this region from 4 to 5 centimeters, look, this slope here of the potential, that's a positive slope going uphill. but the electrical potential is a negative slope of the electrical potential, and so it's a negative of a positive. So in this region here, from 4 to 5 centimeters, the electrical field is minus 30 volts per centimeter. So I think it's this bottom one here, positive in this region, the field, negative in this region, the field. Any questions on that? Okay, that's good. You know, I'm thinking all the time in teaching now that somehow I'm being gravitationally pulled over to this side of the room, and I'm feeling bad for this side of the room because I'm always kind of looking over here. So I've got to stop doing that, but I'm always looking at this slide. So anyway, that was just a little interlude of personally revealing something. What are you have already asked this question? What you just wanted to know straight off, not all this sort of other talk. What is the electrical potential of a positive charge? What is the electrical potential of the negative charge? Those are the building blocks of our landscape of electrical potential. We better know that, because every electrical potential landscape is built out of those things. Well, here's the answer, and I've got several ways of picturing it. Here's the answers to the question of what is the electrical potential of a point charge. I've drawn them for the electrical potential of a positive charge, which creates a positive potential. But, you know, the negative charge looks the same. It's just a negative potential for a negative charge. So I've drawn just cases of the positive potential. So on this figure here, I've actually plotted both the electrical field strength and the electrical potential. So I could compare them. That's the vertical axis. And I'm plotting the field and potential as a function of the distance from a positive point charge. So that's the horizontal axis. The field that we've met before is indicated in orange here, and that's the field that for a positive charge, remember it fell off as the inverse square of the distance. So that's what the field looked like, and it was in proportion to the size of the charge. More charge, more field, less charge, less field. The new thing, new person, is the electrical potential here. This is, in blue, the electrical potential of the point charge. It also falls off with distance, maybe not surprisingly, but it falls off just as the inverse of the distance, not the inverse square of the distance. So that's the difference. It's in proportion to the charge, here's Q, just like the field was in proportion to the charge. So again, if you make the charge bigger, you'll make both the field and the potential bigger. If you make the charge smaller, you make both the field and the potential smaller. And so this just compares these two things. On this plot, the electrical field, which is in orange, is actually the negative slope of the electrical potential. So this plot kind of embodies that relationship we described between field and potential. The field is negative slope of potential. Look, the potential is sloping downhill, and so that's a negative slope. And so the electrical field is going to be a positive field because it's the negative slope of the potential. And you see this is a positive field. If I had made this drawing, which I did not do, for the negative charge, then surrounding the negative charge has a valley of electrical potential. The slope, as you walk away from it, of the electrical potential is uphill. That would mean that the field would be in the opposite direction. It's the negative slope, which would mean the field would be towards the negative charge, which is, we know that's the case. So that relationship between the field being the negative slope of the potential holds, you know, for the positive charge, holds for the negative charge, holds for any arrangement of charges. Here's a way that we often picture the field, and also, this is a new thing, a way that we often picture the electrical potential. And this is how we picture the field, how we picture the potential for again, a positive point charge. A positive point charge is right over here in the center. And I've drawn the electrical field as field lines surrounding it. Remember, they're packed together closely near the charge. They're packed together loosely far from the charge. They indicate the strength of the field being strong if they're closely packed, the field being weak if they're loosely packed, and they indicate the direction of the field through their arrows, through their directions. The new thing on this slide, though, is these blue contours, these blue dashed lines. That's how we picture an electrical potential. Now, electrical potential is not a vector. It doesn't have a direction to it. It can have a plus or a minus sign, but it doesn't have a direction to it. So it just has a sign, a size, and everywhere on a particular contour has the same electrical potential. So that's the meaning of a contour of electrical potential. We even call them equipotential contours, meaning equal potential contours. So, for example, on this contour here, which looks like a circle, but really it's a three-dimensional sphere surrounding this positive charge, everywhere the electrical potential is the same. So maybe everywhere on this contour, the potential is, I don't know, make it up, 4 volts. So that's the contour of 4 volts. A little further from the charge, this contour, maybe that's the contour of 3 volts. The potential's gone down, we're further from the charge, further from the positive charge. So here's the contour of 3 volts. This might be the contour of 2 volts. Everywhere on that circle, which is really a sphere, the potential on that equipotential surface is 2 volts. And the same thing down here on this big circle that I just managed to squeeze in. Everywhere on that, the electrical potential is the same, 1 volt. And so that's how we visualize the electrical potential landscape. We actually make electrical contours, equipotential contours, that describe the landscape. And actually that's done with maps of the Earth too. You can see elevation maps that use contours to describe not the height or depth of an electrical potential, but the height or depth of the Earth above sea level. So same sort of way of picturing, same sort of way of imagining the electrical potential landscape as a real landscape. I mean, it is a real landscape, but as a real concrete landscape. Here's another way we could picture it, 3-dimensionally, on a 2-dimensional plot. So on this plot, here's a positive charge right at the center of this diagram. Out of the screen towards you, I've got the x-axis, so 1 dimension of space. From left to right, I've got another axis. That's the y-axis, a second dimension of space. Vertically, I'm plotting now the potential. So this is a 3-dimensional diagram. 2 space dimensions in the horizontal plane, 1 towards you, 1 over here towards the right, and then 1 vertical direction for the potential itself. Here we clearly see the positive charge being a mountain. It's a mountain of electrical potential. A negative charge would be a well or a valley of electrical potential. So we see that feature. We also, as shown on this picture, this is kind of clever, the authors of this picture wanted to show us the relationship to the electrical field. And they did it with the colors on the picture. So they color-coded different regions on this picture of the contours of electrical potential with the slopes. Red indicates a very steep slope. Blue indicates a much shallower slope. Yellow is some in-between slope. So very close to the positive charge, you see the slope is steep, which means a strong electrical field, which is of course the case. Very far from the electrical charge, down here, you see this blue indicates a small slope. So that's a weak electrical field, which is of course the case, far from the positive charge. So all that's contained in that figure. Here's, I got 2 more pictures here, I think. I want to show you just a more complicated arrangement. We've been looking at pictures, sketches of the electrical potential, electrical field of a single positive charge. The single negative charge looks very similar in terms of potentials and fields. It's just the field lines go in rather than out. It's just that the potential is a well rather than a mountain. This example here and the next example here are the electrical fields and electrical potentials of an electrical dipole. Remember, that's the famous building block of, famous characteristic of water that gives water its fabulous properties. Okay, so here's the positive charge of the dipole, here's the negative charge of the dipole. The dipole is opposite charges separated by some distance. In orange here, we've seen this picture before, here are the field lines that emerge from the positive charge, like a faucet of field lines, and eventually, sooner or later, they return to the negative charge, which is the drain for the field lines. So source and sink. We see a lot of field lines emerging from the positive charge and curling around, either rather quickly or much more slowly, to the negative charge. Even these ones that head off the screen on the left, right? If I had a bigger screen, I could have put up a bigger slide, and you would see that these ones on the left, this one going over here, actually went right around here and came back over here. So they're all going to come back round sooner or later. And so that's the field of the electrical dipole. But on it, I've added the electrical potential. So I've added contours of electrical potential. So the dashed blue lines represent regions where the electrical potential is the same. Everywhere on this line here, the electrical potential is, say, 3 volts. As we walk around here. Everywhere on this dashed blue line here, the electrical potential, remember this is a well, maybe it's minus 3 volts. This one might be positive 1 volt. This might be negative 1 volt. Actually, this one's an interesting one here. That's the midplane. That's 0 volts, halfway between the positive and negative charge. So that's how we draw the potentials. And here's a three-dimensional picture of it. I won't go into this in any detail, but here's like the mountain of the positive charge. That's a big feature in our electrical landscape here. Here's the valley, the well of the negative charge, the other big feature in this landscape. And this is the electrical landscape in this electrical world of mountains and valleys. And we're even shown again through the color coding where the slopes are steep, where the slopes are shallow. What is the electrical field? What's the relationship to the electrical field? Okay. I'm moving on quickly because I'm getting panicked by the clock. So let's move on to some examples. Let's try and do some examples. And here's an example. In this example, we've got 2 charges. There's one on the left, it's 5 nanocoulombs. There's another one on the right, it's minus 3 nanocoulombs. And we're asked to figure out a couple of things, given those charges and the fact that they're 35 centimeters apart. So kind of like this. We've got to figure out the electrical potential at the midpoint of the charges, and we've got to figure out the potential energy of the arrangement of charges. So those 2 things. So I'm going to do those 2 things. I'm going to do it, I think, on the, despite the fact that it will cost me some time, which makes me panic even more, I'm going to do it on the device I can't remember the name of, the thing here. Okay, here we are. What was the first question? The first question was, in this arrangement of charges, which I've actually drawn already to save me some time, I've got to figure out the potential at the midpoint. So the midpoint is somewhere here. But what's that potential going to be? Well, this is a good example of a property of potentials. that is similar to the property of fields, which is similar to the property of forces in electricity, that potentials superimpose, like fields superimpose, like forces superimpose. So the potential V at that location is just the potential due to the charge on the left. That was called Q1, so I'm going to call its potential V1, plus the potential due to the charge on the right. I'll call that V2 because that was charge number 2. So that's superposition. That's the idea of superposition. But I love superposition with electrical potentials. Why do I have that feeling? Why would I like that? The reason I like that is with electrical fields and forces, superposition means you add together the fields or the forces, but you're adding together vectors. And adding together vectors is costly in terms of time. You've got to worry about the sizes and the directions. Adding together potentials, this is the beauty of potential. Adding together potentials, they're just numbers. I mean, they might be positive or negative, but they're just numbers to add together. So this is going to be way easier. This is why I can solve this question in a few minutes rather than in 15. Okay, potential of charge number 1. Well, we had an equation for it, didn't we? We had an equation that it was KQ over R. So I'm going to call that K1 Q1 over R1 because I'm talking about the first charge. And I'm going to then add the electrical potential of the second charge. That's KQ2 over R2. So I've just got to add those together. And if I do the sum, I'm going to pull out a factor of k that's a common factor. So that's 9 times 10 to the 9. I'm going to not write down the units because that's naughty. Don't do this on an exam, but I am panicked because I'm running out of time. So I'm going to ignore the units for now. I'll come back to them at the end. And I'm going to fill in the charges. We've got 5 times 10 to the minus 9. That's the 5 nanocoulombs. We've got a distance. It's not 35 centimeters. It's half of that because this point is halfway between the two. So 0.75 meters, 175 meters. I don't know why I wrote the M. I'm not doing that. And then I've got the charge divided by the distance for the other charge, Q2. That's minus 3 times 10 to the minus 9 coulombs, but I'm not writing that down. And I've got that divided by half the distance between the charges. That's 0.175. And if I work out that calculation, my 10 to the 9s cancel out. That's kind of handy. And what did I get? Can't read my own writing, but I got 103 volts. The positive charge was a bigger charge. So positive's going to win over negative. The negative charge was a smaller charge. So it makes sense that it's positive charge. And 9 times this quantity in parentheses gives you 103 volts. So that's how we figured the electrical potential. And that's combined superposition principle with our understanding of potentials of point charges. Right, I need to do the second part of this problem. What is the energy stored by this arrangement of charges? Well, that's an interesting question. The energy stored by the arrangement of charges, one way of thinking about it is to imagine bringing up the two charges individually and putting them at those locations. Now, let me pull this back down. Imagine I bring up charge Q1 and place it on the screen at that location. So that's the first thing I'm going to do. And then imagine I bring this other charge up, charge number 2, and place it at this neighboring location. So that's what I'm going to visualize I'm going to imagine assembling the charge distribution to figure out the energy that it's stored. How much change in potential energy? I'm going to call it delta for change, PE for potential energy, 1 because I'm referring to charge number 1. How much change in potential energy was there when I brought up the first charge? How much change? There's actually none. There's no charges around. when I bring up the first charge. It's just like empty space. There's no fields and potentials around. It's just an empty landscape. And so when I bring up the first charge and place it on the left, there's actually no work that I have to do. I don't have to push it or pull it. I have to do no work. I transfer no energy. It acquires there's no change in electrical potential energy. So this guy is easy. Change in potential energy for charge number 1 is 0 when I bring it up. But now it's different for charge number 2. Because charge number 2, when I bring it up on the right, it's going to be brought up in the neighborhood of charge number 1. So there is going to be a change in electrical potential energy. Either I'm going to have to add energy to pull that charge in, or as I pull that charge in, it's going to release energy. So let's figure that out. And to figure that out, all we need is that relationship. Really, it's the definition of electrical potential. So let me write it down. It's this relationship here. The change in potential energy of charge number 2, that's the one on the right, when I bring it up, is equal to the product of the charge number, let's see, I've got this the wrong way around. I'm doing it wrong myself. Gosh. I really messed it up. I'm kind of thinking now, this door's kind of close. I could just run out. But I'm not. Okay, so this is going to be a 2. The change in potential energy, but when I bring up charge number 2, what's that change in potential energy? The change in potential energy, when I move charge number 2 in a landscape of electrical potential, the change in potential energy is the change in potential that I moved it through times the value of its charge. This equation here was a definition, the equation we used to define electrical potential. Except that now, instead of it referring to a test charge, the energy of a test charge, and the amount of charge owned by the test charge, it's now referring to charge number 2. Charge number 2 has kind of become our test charge. Now, this is not 0, right? Because charge number 2 is sitting in the electrical potential of charge number 1 when we bring it close up. So I've got to multiply, God, I keep writing 1s here. Charge number 2 by KQ1 over R. This is the electrical potential of charge number 1 at that location where we place charge number 2. Okay, so if I filled in all those numbers, I'm not going to write them all down. The 2 charges, the distance between the charges, and the Coulomb constant, that tells me that the change in electrical potential of charge number 2, when I bring it close to charge number 1, is minus 3.9 times 10 to the minus 7 joules. So that's the change in electrical potential energy. It's negative. And it's negative because I brought a negative charge in proximity to a positive charge. If you bring a negative charge in proximity to a they're attracted. They're attracted to one another. And so just like, if you drop an apple towards the earth, it's going to release electrical potential, gravitational potential energy. This is releasing electrical energy. Okay. We're almost there. Thank God. Total change in potential energy, which is, the amount of work that I did to build this arrangement of charges. The amount of energy that it's storing is the sum of these two. And the sum of these two is simple. One of them 0, and the other one is minus 3.9 times 10 to the minus 7 joules. And so that is the energy that's stored by this arrangement. It's negative 3.9 times 10 to the minus 7 joules. What that means is, supposing you wanted to pull those 2 charges apart. To pull those 2 charges apart, you would have to you would have to add energy. You'd have to tear them apart because they're attracted to one another. One's positive, one's negative. It's just like an atom. Suppose you got a hydrogen atom. That's a negative charge and positive charge. Break up a hydrogen atom, you'd have to add some energy to pull apart the charges. To break up this atom, you'd have to add some energy to break apart Q1 and Q2. Okay. Oh, where am I going? Nobody knows. Wanted to look at one more example. I was going to do this on the light pen, but or the whatever this thing's called, but I don't think I will now because I think there's not a hope in hell that I can write that fast. Gravity versus electricity. I want to make a remark about that and then show you an example. So I drew that analogy between gravity and electricity. Electric and gravitational fields, electric and gravitational potentials. But there is an important difference. Gravity is always attractive. Masses always attract other masses. Whereas electricity, charges can attract or repel depending on whether they're positive and negative charges. That's a big difference. Masses always moved closer, are always attracted to one another. And when they're attracted to one another, they release energy. So if you drop a ball towards the ground, the ball is attracted toward Earth, it's going to release energy. In the case of charges, positive and negative charges, if opposite charges come together, they're attracted to one another, that's also going to release energy. Just like a 5 nanocoulomb and minus 3 nanocoulomb charges. But if you've got like charges repel one another. So to push two like charges together, you've got to add energy. You've got to do work to move those charges together, fighting against their repulsion. So that's a big difference. There's another big difference here, and I want to show you on this picture. On this picture, I'm showing you a region of electrical field. I've made it with this wall of positive charge on the left, and I made it with this wall of negative charge on the right. And you see the electrical field lines streaming from the positive charges between the negative charges, as you'd expect. I also added lines, these light dashed blue lines here, vertical lines, that are equipotentials, contours of equal electrical potential. So this might be plus 1 volt, this might be minus 1 volt over here on the left and right. I wanted to make a point. Okay, so the electrical potential slopes from it's a hill on the left, it's a valley on the right. So it slopes downhill from left to right. If you release a positive charge up here, over here, then that positive charge will roll down the electrical potential hill. It's being repelled by the positive charge on the left, attracted by the negative charge on the right. If we release a negative charge, it actually rolls up. It's natural for it to roll up the potential hill. So that's an important difference. You see this negative charge, it's rolling up the potential hill. It's being repelled by the negative charges, the like charges on the left, and it's being attracted by the positive charges on the right. And so that's an important thing to bear in mind, this complication with electrical potentials that makes it quite different, distinct from gravitational potentials. So this is the positive charge in red, this is the negative charge in green. This is the landscape of electrical potential between the positive brick wall and the negative brick wall. This red positive charge would roll down that potential hill. But remember, you've got to imagine this negative green charge rolling up the potential hill. This is being repelled from like charges, the positive ones on the left. This is being repelled by like charges, the negative ones on the right. Anyway, I'm going to end there. On our Canvas module, there's another example of this problem that I didn't get to in class, but I would encourage you to look at it there. Yeah.
Okay, the first one is, I think I just forgot probably, but why is this a negative